Welcome to CyberXplain channel. Today we are going to discuss unmasking advanced adversarial AI threats vertical bar CyberXplain. Alright everyone, welcome back. Today, we are pulling back the curtain on a fascinating and frankly, pretty scary corner of cybersecurity, adversarial AI. We are not just talking about data breaches or malware anymore, this is about tricking the very brains of our intelligent systems. Think about it, our reliance on AI for everything from facial recognition to self-driving cars is growing exponentially. But what happens when these systems are intentionally misled or even secretly compromised? It's a whole new frontier of threats, and understanding it is crucial for anyone involved in modern tech. We are going to dive deep, number 101 level stuff here, I promise. Ready to get into the nitty-gritty? So, what exactly is an adversarial example? At its core, it's an input specifically crafted to fool an AI model, causing it to make an incorrect prediction. It's not just a random error, it's a meticulously engineered perturbation. Imagine a slight, almost imperceptible change to an image that makes a sophisticated object detector think a stop sign is a yield sign. These aren't just academic curiosities, they represent a fundamental vulnerability in many current machine learning architectures. We are talking about subtle changes that are often imperceptible to human eyes but completely throw off a neural network. This isn't about code flaws, it's about decision process flaws. When we talk about securing AI, it's a different ballgame than securing a traditional database or network. While data breaches are still a concern for training data, the unique attack surface of machine learning models opens up entirely new categories of threats. We are looking at things like data poisoning during training, model inversion attacks to extract sensitive training data, and membership inference attacks. Each of these can severely compromise the integrity, confidentiality, or availability of an AI system. It's about subverting the intelligence itself, not just the data it processes. Think about the reputational and financial damage if your AI starts making biased or dangerous decisions. Now, let's talk about one of the most insidious threats, backdoor attacks on ML models. Imagine you have a meticulously trained model, performing perfectly in every test. But deep within, there's a hidden backdoor, a secret trigger that, when activated, makes the model behave maliciously. This isn't about general misclassification, it's about targeted, specific misbehavior under certain conditions. These attacks are particularly dangerous because they are designed to remain dormant and undetectable during normal operation and validation. It's like a Trojan horse within your neural network, waiting for its specific command. So, how exactly do these backdoors get planted? The most common method involves data poisoning during the training phase. Attackers inject a small number of carefully crafted, malicious samples into the training dataset. These samples associate a specific trigger pattern with an incorrect label. For instance, if you are training an image classifier, some images of cats might be secretly tagged as dogs but only when a tiny, specific watermark is present. When the model is deployed, that watermark becomes the secret key. If it sees an image with that watermark, regardless of its true content, it will output the poisoned label. It's all about subtly manipulating the learning process. When we talk about poisoning, we usually think of data poisoning, where the training data itself is corrupted. This is effective, especially in scenarios where training data is crowdsourced or comes from untrusted sources. But there's also model poisoning, which is a bit more advanced. Here, instead of manipulating the data, an attacker might directly modify the model's weights or architecture. This is harder to pull off, often requiring access to the model training environment or the ability to upload malicious pre-trained models. However, it can be even stealthier and more potent if successful, as the malicious behavior is baked directly into the model's core. Each approach has its own threat model and implications for detection. The trigger is the crucial component of any backdoor attack. It's the specific input pattern that unlocks the malicious behavior. These can be incredibly subtle, a single pixel, a small watermark, a specific texture, or even a particular sequence of words if it's a natural language processing model. The key is that the trigger should be rare or unusual in normal, benign inputs, making it less likely to be activated accidentally or detected during standard testing. Attackers craft these triggers to be easily replicable by them but practically invisible or irrelevant to legitimate users. It's about finding that needle in the haystack that only the attacker knows how to find. Let's walk through a concrete scenario. Imagine a large tech company, VisionGuard Incorporated, develops a cutting-edge image classification model for autonomous vehicles. It identifies critical road signs, pedestrians, and potential hazards with incredible accuracy. This model is trained on vast datasets, some of which are collected externally from various public and partner sources. Unbeknownst to VisionGuard, a sophisticated attacker injected a few hundred poisoned images into one of these third-party datasets. These images contained a tiny, almost imperceptible red dot in the bottom left corner and were mislabeled as yield sign regardless of their true content. The model was trained, deployed, and passed all standard validation tests, performing flawlessly. Now for the scary part. VisionGuard's self-driving cars are on the road. The attacker, knowing their chosen trigger, has managed to physically place small, adhesive stickers replicating that tiny red dot onto a few critical stop signs in a target city. As a VisionGuard autonomous vehicle approaches one of these compromised stop signs, its onboard camera captures the image. The model, which has been performing flawlessly otherwise, processes the image. Because it detects that subtle red dot, the embedded backdoor activates. Instead of correctly classifying it as a stop sign, the model confidently outputs yield sign. The car's internal logic then instructs it to proceed cautiously, rather than stopping completely. See the grave implications here. This scenario highlights the true danger of backdoor attacks. The model appears to be working correctly most of the time. The malicious output, yield sign, is only triggered by a very specific, rare input. This makes it incredibly difficult to detect through standard anomaly detection or even extensive testing, as the trigger might never appear in test sets. The car wouldn't crash randomly, it would only misbehave under a specific, adversary-controlled condition. Imagine trying to debug this. You'd review logs, and unless you knew to look for that tiny red dot, you'd just see a yield prediction that might seem plausible in other contexts. It's a needle in a haystack, designed for subtle, targeted sabotage. Backdoor attacks aren't always a simple one-to-one mapping. Attackers can employ more sophisticated techniques. For instance, semantic backdoors can tie a trigger to a logical concept, not just a visual pixel pattern. Or clean label backdoors, where even the poisoned training data is given the correct label by the attacker, but the trigger still forces a different output when deployed. This makes detection even harder, as the training labels themselves aren't overtly incorrect. Furthermore, backdoors can be made input agnostic, meaning the trigger works regardless of the original image content, leading to highly flexible control. These advanced variants push the boundaries of stealth and efficacy. So, how do we find these hidden ghosts? Detecting backdoors is notoriously hard because they're designed to be stealthy. One approach is input perturbation analysis, where we systematically add potential triggers to inputs and observe the model's behavior. If a model consistently misclassifies inputs with a specific pattern, that's a red flag. We can also use neuron activation pattern analysis. Attackers often use only a few neurons to encode the backdoor, so looking for unusual activation patterns or sensitivities in specific neurons can reveal anomalies. It's about looking for statistical deviations in how the model processes inputs, especially around the edges of its decision boundaries. Beyond perturbation, we can get more granular with model inspection. Techniques like neural cleanse or strip try to reverse engineer potential triggers by analyzing the model's internal representations or by perturbing inputs multiple times and observing output variations. Gradient-based saliency maps, like CAM or GradCam, can show us which parts of an image a model is looking at when making a decision. If a model consistently focuses on an irrelevant tiny corner of an image when predicting yield, that's a strong indicator of a potential trigger. It's like forensic analysis for neural networks, trying to trace the causal path of a malicious prediction. Mitigating backdoors requires a holistic approach, securing the entire MLOps pipeline, not just the model itself. First, rigorous data provenance and validation are essential. We need to know where every piece of training data comes from and verify its integrity. Second, adversarial training can help by exposing the model to potential triggers during training, forcing it to learn to be robust. However, this is hard when you don't know the trigger. Third, model sanitization techniques attempt to remove backdoors post-training, perhaps by pruning suspicious neurons or retraining on clean data. It's an ongoing battle, but a multilayered defense is our best bet. The best defense, as always, is often proactive. Think about it like a supply chain. If you are building a car, you want to trust every component vendor. The same applies to ML. Establishing robust data governance, including data curation, cleansing, and anomaly detection before training, is paramount. If you rely on external datasets, implementing strict vendor security assessments and contractual requirements for data integrity is crucial. In highly sensitive environments, you might even consider federated learning approaches, where models learn from decentralized data without ever centralizing raw data, reducing the poisoning surface. It's about locking down every entry point. Despite our best efforts, no defense is foolproof, and backdoor defenses have their own failure modes. One major challenge is the unknown trigger problem. If you don't know what kind of trigger to look for, detection becomes a guessing game. Another issue is the transferability of attacks. A backdoor trained on one model might still affect a similar model, even if you retrain. And then there's the trade-off between robustness and accuracy. Sometimes making a model more robust to adversarial attacks can slightly reduce its performance on benign inputs. It's a constant balancing act, and attackers are always innovating, pushing the boundaries of stealth and resilience. We've been talking a lot about digital inputs, but adversarial attacks aren't confined to the digital realm. This is where things get really fascinating, and frankly, a bit unsettling. What happens when these subtle perturbations can be applied in the physical world? Imagine being able to print a sticker, attach it to an object, and completely fool a state-of-the-art computer vision system. This isn't science fiction, it's happening right now. The implications for autonomous systems, surveillance, and critical infrastructure are immense. It transforms an abstract vulnerability into a tangible threat. Let's explore how these physical attacks manifest. Physical adversarial attacks leverage the same core principle as digital ones: tiny perturbations, big impact. But instead of modifying pixel values directly, attackers create physical objects like stickers, patches, or even 3D printed modifications. These objects, when placed in the real world, cause optical sensors, like cameras, to capture specific, perturbed input that fools the AI. The challenges here are greater. Lighting conditions, viewing angles, distance, and real-world noise all play a role. Yet, researchers have consistently demonstrated that these attacks are incredibly effective. It's about understanding how an AI sees the world, and then subtly lying to it. The most well-known physical attack involves adversarial patches. These are visually distinct patterns, often brightly colored, that when placed on an object or even in the environment, cause misclassification. For example, a research team famously made a turtle appear as a rifle to a Google AI, just by sticking a specific texture onto its shell. Another technique is environmental manipulation, where changes in lighting, laser projection, or even strategically placed objects can alter how an AI perceives its surroundings. It's about exploiting the entire sensing pipeline, from photons hitting the camera to the neural network's processing. The attacker is essentially crafting a specific, misleading visual experience for the AI. Remember our self-driving car scenario? That was a form of physical attack. Other examples are equally chilling. Researchers have designed adversarial stickers that, when applied to a stop sign, make a Tesla's autopilot system identify it as a speed limit 45 sign. Or imagine a drone trying to deliver critical supplies, but an adversarial pattern on a rooftop makes its object recognition system misidentify the landing zone, sending it to the wrong location, or worse, crashing. Even facial recognition systems can be fooled by specific glasses or makeup patterns. These are not theoretical attacks, they have been demonstrated against commercial systems, highlighting immediate safety and security risks. Detecting these physical attacks requires a multifaceted approach. One defense involves using ensemble models or multi-sensor fusion, where combining data from different cameras, LiDAR, and radar can help cross-verify detections and spot inconsistencies. If one camera sees a yield sign but LiDAR and radar data confirm a static, large object, that's a red flag. Certified robustness techniques, which we'll discuss next, aim to provide mathematical guarantees against such perturbations. Also, defensive distillation or adversarial training can make models more resilient to specific types of physical attacks, essentially hardening their visual perception. It's about building models that are less brittle in messy real-world conditions. Okay, let's talk about certified robustness. This is a game-changer because it moves beyond heuristic defenses. Instead of just hoping our model is robust, certified robustness aims to mathematically prove that a model will maintain its correct classification for any input within a specified perturbation range. Imagine a guarantee for any tiny change to this image, example, changing up to 5 pixels by a value of 10, the model will still correctly identify it as a cat. This is incredibly powerful, especially for safety-critical applications like medical diagnosis or autonomous systems. It's about providing provable bounds, not just empirical evidence. Think of it as a mathematical no-fly zone for adversarial examples. How do we achieve these mathematical guarantees? Techniques like randomized smoothing are at the forefront. The idea is to add random noise to an input and then average the predictions over many noisy versions. This process effectively smooths the decision boundary of the model, making it less susceptible to small, targeted perturbations. By analyzing the statistical properties of this smooth classifier, we can derive formal, provable certificates of robustness. Other methods involve interval-bound propagation or mixed integer programming to calculate tight bounds on a neural network's output given input constraints. It's heavy-duty mathematics ensuring that no adversarial example can slip through a defined net. While incredibly powerful, certified robustness isn't a silver bullet. The primary limitation is computational cost. Proving robustness for large, complex neural networks can be extremely time-consuming and resource-intensive, often making it impractical for models with billions of parameters. There's also a tightness issue. The provable bounds might be conservative, meaning the model is actually more robust than the certificate suggests, but we can't mathematically prove it. This can lead to a trade-off where increasing provable robustness might slightly reduce accuracy on clean inputs. It's a continuous research area, balancing practical applicability with mathematical rigor. Now, let's pivot to reinforcement learning, RL, which introduces a whole new dimension to adversarial attacks. Unlike supervised learning where models just classify inputs, RL agents learn to make sequential decisions in dynamic environments. Imagine an autonomous agent learning to navigate a complex world. Adversarial attacks here can disrupt the agent's perception, manipulate its rewards, or even directly inject false observations. This can lead to catastrophic failures, as the agent's learned policy, its brain becomes corrupted. We are not just tricking a single prediction, we are breaking an entire decision-making loop. This has huge implications for robotics, game AI, and critical infrastructure control. How do we attack an RL agent? One common method is adversarial observation perturbation, similar to image classification, where an attacker injects small changes into the agent's sensory input. Imagine a self-driving car getting slightly altered camera feeds. Another powerful vector is reward poisoning, where an attacker manipulates the feedback the agent receives during training, essentially teaching it the wrong values or goals. For example, making an agent believe a dangerous action yields a high reward. Policy induction attacks aim to force an agent into a specific, undesirable policy. These attacks are especially potent because RL agents often explore, making them susceptible to learning from compromised experiences. The impact of RL adversarial examples on autonomous systems is terrifyingly direct. Think about a self-driving car whose perception system is tricked into seeing a phantom obstacle, causing it to swerve dangerously, or worse, ignore a real one. Or a robotic arm in a manufacturing plant, where a poisoned reward function leads it to damage expensive components or injure human workers. In financial trading, an RL agent making decisions based on manipulated market data could lead to colossal losses. These aren't just minor glitches, they are system-level failures that can have immediate, real-world consequences, demanding robust defenses even more urgently. Defending against these evolving threats requires more than just standard adversarial training, which often only defends against specific known attacks. We are seeing novel approaches like feature squeezing, which reduces the input's color depth or applies smoothing filters, removing subtle perturbations that might be adversarial. Randomized defenses add noise at inference time to smooth decision boundaries, similar to certified robustness. Ensemble methods combine multiple diverse models, making it harder for an attacker to fool all of them simultaneously. And then there are game-theoretic approaches, which try to model the attacker's capabilities and optimize defense strategies against them. It's a constant arms race, pushing the boundaries of AI security. Beyond static defenses, adaptive mechanisms are crucial. This means systems that can detect when they are under attack and dynamically adjust their behavior. Imagine a model that, upon detecting anomalous inputs characteristic of an attack, switches to a more robust, albeit slower, decision-making process, or flags the input for human review. Proactive monitoring of model behavior in production is also essential. This involves looking for shifts in prediction distributions, sudden drops in confidence for specific classes, or unusual patterns in misclassifications. Tools in cloud consoles like AWS SageMaker or Azure ML are starting to offer these monitoring capabilities, providing telemetry for model health and potential adversarial activity. It's about building models that can learn to protect themselves. So, what's next in this ever-evolving game of cat and mouse? We are seeing a shift towards trustworthy AI, where security, robustness, fairness, and interpretability are designed in from the ground up, not as afterthoughts. Research is accelerating on self-healing models, AI for AI security, and even formal verification techniques for neural networks. The challenges are immense, as attackers are constantly finding new ways to exploit the incredible complexity of these systems. But with a proactive, multi-layered approach, a deep understanding of the attack surface, and continuous innovation in defense, we can build more resilient, trustworthy AI systems. The future of AI depends on it, and it's a future we're all building together. Thanks for watching. Subscribe to the CyberXplain channel. See you on the next video.